Hello, everyone. Welcome back. Good morning. And let's get started. Sorry, we had a few minutes delay here. So we have another interesting session prepared for you today. Our next speaker brings a perspective that's very, very important these days. How do you move quantum software research from kind of the research area into more real-world financial applications? And we have with us Tom Finke, who's the CEO and co-founder of Applied Quantum Software, where he leads work on quantum computing solutions for the financial industry. He helps financial professionals explore practical uses of quantum algorithms, market data, and quantum computing platforms. His background spans some of the most respected names in finance and technology, including BlackRock, One Market Data, and Visa. And his academic training includes electrical engineering at Stanford and computer engineering at USC. And today, Tom is going to bring us a perspective from the practitioner side on how quantum software is kind of beginning to find its footing and in one of the most demanding real world applications and in financial markets. So please join me in welcoming Tom. Over to you, Tom.
Great. Thanks, Abhinaya. Hey, good morning, everybody. Thanks so much for having me here. Actually, it's not just me. One of our other co-founders of our company is also going to join us. So I think what we'll do is I'll speak for maybe 10 or 15 minutes. And then our co-founder, Jun Dao, will also speak for maybe 10 minutes. And then we'll open it up for Q&A and we'll see how long we can go until we exhaust your questions. So good morning. It's morning here in San Francisco. I'm Tom Finke, co-founder and CEO of Applied Quantum Software, or AQS. We do quantum computing for enterprise finance. So we are applying the capabilities of quantum computing approaches for applications that are relevant to the finance industry. And you'll see why in a moment why we have selected that vertical. But first, it's always important to introduce the team because people are always the most important asset in a company. So at our company, AQS, we actually have 4 co-founders. So I am Tom Finke, the co-founder and CEO. We also have Matt Lee, the CSO, Jundao Zhuang, our CTO, and Floyd Smith, our CMO. And each of us bring strengths to our founding team such that we end up with a really strong foundation and a balanced team. So Matt and I met years ago working at BlackRock, and I'll actually give you a really short, funny anecdote story about how we started up this company. So we're both pretty technical people. Matt has a PhD in quantum physics, and he was the managing director of a large research team at BlackRock, a quantitative research team. And I led the technology teams who built the systems that his group used, and also a lot of other groups at BlackRock. And a few years ago, actually on Star Wars Day, which is May the 4th, so on May the 4th, there was a lecture on quantum computing in San Francisco, and Matt and I went to that lecture several years ago. And ever since that time, we thought to ourselves, this quantum computing stuff is absolutely fascinating. We should really think about applying this to our work. And little did we realize that a couple of years later, we would actually start a company that's doing quantum computing specifically for finance. So that's why really we're focusing first on finance, because that is our background. That's our area of expertise. That's the industry we're coming from. So it really makes sense for us to jump in with the finance application. But even though Matt himself has a PhD in quantum physics, he didn't have deep expertise in quantum computing, but our co-founder Jun Dao does. He's actually a professor of quantum computing at USC, and so we're connected through grad school. So he's our third co-founder, and our fourth, Floyd, he's the co-author of the book Quantum Computing for Dummies. So those dummies books that are really good at explaining complex concepts. He's the author of the quantum computing book. So together, we're a really strong, balanced team, each with our own strengths that we're bringing to the table. So there's an introduction to our team. So a little bit more on why finance. Why is the finance industry appropriate for solutions in quantum computing? There are several different reasons. One is in quantitative finance, there is a lot of pretty advanced math in terms of probability, combinatorial optimization. All of these mathematical disciplines funnel into solutions for our customers in quantitative finance. And you, you're probably not surprised to know that billions of dollars are spent in research in the finance industry every year. So even a small improvement, even a small edge in speed or accuracy can end up giving our customers a huge competitive advantage. So quantum computing is poised to provide those types of advantages. So that's why we're jumping in. And third, this is also interesting.
Sorry to interrupt you, Tom.
Yeah.
Were you like going to share your screen?
Yes, I thought that I was, and I will do so
No,
now.
sorry. Yep.
All right, let me do that. In that case, you haven't seen the slides I've been showing, so I will do that real quick. All right, thanks for reminding me. So, just backing up slightly, this is our title slide. So, applied quantum software, and our talk today is about quantum computing and the future of finance. And I had just spoken about our four co-founders at Applied Quantum Software. So here's that slide. And then I was just getting into this slide, which is the opportunity that quantum computing provides for the finance vertical. So I'm just double checking. Can you see my slides now?
Yeah, all good. Thank you.
Okay, great. So, all right, sorry, I thought you'd been able to see my slides. So I was just going through the math and then the value proposition, and here we are. Okay, so we were talking about the kinds of problems that are amenable to quantum computing solutions. It happens that the kinds of quantitative finance problems that we're looking at are appropriate for quantum computing. And one reason why is because in some of these quantitative finance applications, you don't really need exact answers. You can have a range, a probability distribution of answers, and that is sufficient to get you to the solutions that you're seeking. So when we're saying approximation tolerant, that's what we mean. And you'll see when we talk a little bit more about how quantum computers work, how that fits in. So next slide. So we do need to level set a little bit because quantum computing is a very complex topic. So just want to provide some of the highest level concepts so that we're all on the same page. So you've probably heard of bits in the classical world, computing bits. In the quantum world, they're called qubits. So that stands for quantum bit. And qubits really provide the amazing power behind the solutions that quantum computers can provide. And I don't want to jump too deep into the quantum physics, but I really do want to mention three properties of qubits that give us this amazing potential speed up that we're getting from quantum computers. The first is superposition. That means that these qubits can be in a state of being somewhere between a 0 and a 1. And when you measure the qubit, it will collapse into one of those two states, a 0 or a 1. The second is entanglement. And that means if you have two qubits, two or more qubits, that if you do something to one of them, it will immediately affect the other one. And we can harness that capability to improve the parallel processing of the quantum computing solutions. And finally, interference. This is a means where we can increase the probability that the correct answers will come out of the computer and decrease the probability that the incorrect answers won't come out so that the correct answers will end up reinforcing each other like ripples on like the ripples of waves on a pond where they come together and reinforce each other. So that's about the highest level introduction to quantum computing I can think of to provide, but I just wanted to give you that overview. And the second idea here is, well, what is it about quantum computing that's actually better? And it kind of boils down to either speed or quality. So using those properties of the qubits that I just discussed, you can end up doing your calculations either faster or because you can explore more of the range of the space of possible solutions, you can also potentially get more accurate or more precise answers than you otherwise could using classical approaches. And on this plot, you've probably heard of one of the applications of quantum computing about breaking encryption. That is not what we do, but on this plot, it's showing this dashed blue line is the as the size of the problem gets bigger, the ability for classical solutions to solve the problem gets worse, but using a quantum computer, the ability is becomes much more manageable. So I know, let's look at this. This red line is for factoring large numbers in a classical way, but if you do it in a quantum way, represented by the dashed blue line, you can get your answer much sooner. And that's really underlying the reason why eventually it's true that quantum computers will be able to break the types of encryption that are in place today. But for us, with our applications in finance, we are focusing more on improving the types of calculations that go into financial applications. And in many ways, it boils down to a speed up that we get that's called a quadratic speed up. So that means in the classical world, if you solve a problem and then you translate that problem into the quantum world, however long it took in the classical world would take the square root of that amount of time in the quantum world. And you can imagine if you can do something that much faster, then you're going to definitely have an advantage in the types of problems that you want to solve. So let's move along. I did want to mention a little bit about our company, AQS, and what we do. In this diagram, right in the center, we have a box that represents our platform. So the AQS platform is called Fabric with a Q at the end, and we are connecting existing financial market data infrastructure. So the existing infrastructure at large or at financial firms, so that would include their market data, their risk analytic systems, all of their classical systems, and we are connecting them with quantum computing platforms. So in this diagram, the existing platforms are represented by the gray box, the quantum platforms are represented by the purple box, and we provide the infrastructure that connects the two. And one approach or one goal that Matt and I have coming actually from the finance industry, from BlackRock, is that we really wanted to build a platform that is something that we ourselves would want to use. So it needs to be easy, user-friendly, don't need to know anything about quantum physics. We just want to enable our end users, who are finance professionals, to run their use cases and basically flip a switch to run it from on a classical platform to a quantum platform and not have to worry about any of the complexities of the quantum. They just want the answers. So they just want those answers either faster or better or cheaper. And that is what our platform, the AQS Fabric platform, provides. And then just a couple more items about our company in general. We recently, just last month, graduated from a startup accelerator program because we are still a startup. And that program is called Creative Destruction Lab, based mostly in Canada. And they are wonderful because they have incubated and launched more quantum startups than any other accelerator in the world. So it definitely makes sense for a company like ours to go through a program like theirs. And I also want to mention we have a couple of customers, pilot customers, because we're based in San Francisco. We're working with a regulated quantitative hedge fund that's based in San Francisco. So they are a design partner for us to help us achieve our product market fit. And then finally, we have a great collaboration right now with UC Berkeley. So arguably, UC Berkeley has the strongest graduate program in financial engineering in the US. So they are using our Fabric platform as a teaching tool. And also we are working with interns from their program to help move us forward with our research. And they also get to learn a lot about quantum finance approaches, quantum approaches to quantitative finance. So definitely a win-win relationship with UC Berkeley. Okay, this slide is probably the most technical, but I really want to share with you some of the actual use cases and algorithms that we are researching and that we support at Applied Quantum Software. So we've separated this into four different categories of use cases that are relevant for finance: market risk, the pricing of derivatives, optimization of portfolios, and different measures of credit and fraud risk. So these are four general buckets of applications in finance that we support. And within each of those buckets, we have classical solutions, quantum solutions, and also sort of a hybrid that's in between classical and quantum called quantum inspired solutions. And that means we're using algorithms that are based on quantum technology, but we're actually running them on classical computers. So it's a nice bridge between today's classical computing environments and tomorrow's reliable quantum environments. It's a way to implement quantum solutions now while we're waiting for quantum computers to actually mature. So I'm not going to read all of these items, but because I know at Wiser, we've been looking a lot at optimization approaches, I'll just let you know that with portfolio optimization, in case you're interested, some of the quantum algorithms that we've been using to solve problems in portfolio optimization are called QAOA, the quantum approximate or optimization algorithm. There's another one called the variational quantum eigensolver, and there's also a Grover adaptive search. So remember earlier I mentioned we're striving for a quadratic speedup with some of these quantum solutions. The quantum algorithm that gives us that quadratic speedup is called Grover's algorithm. So that's where this Grover adaptive search kicks in. And the last thing I'll mention on this slide is we are trying to be quite rigorous in the way we benchmark today's existing classical algorithms versus the quantum algorithms. So that's why for all of these categories, we have classical counterparts for each of the algorithms so that we can compare that what we're getting now and what we'll eventually get with fault-tolerant quantum computers is actually better than what you could otherwise get with a classical approach. So moving along, actually digging into one of these algorithms. In this plot, I wanted to share like what exactly is it that the quantum approach is giving you that's better than the classical approach. So if you have a distribution, and in this case, the distribution on the x-axis is the return of a portfolio, the financial return. What we can do with quantum approaches is give you a better measure of risk than you might otherwise get with just a classical approach. So what's happening in this plot is the classical approach is given with the yellow dashed line, and the quantum approach is given with the green line. And if you look closely at this plot, you can see that the green line is giving you a fatter tail. It's giving you more insight into the kind of risk that your portfolio is taking on that you wouldn't otherwise know if you were just using a classical approach. So the quantum approach is giving you more information that you as a finance professional can act on to make better decisions regarding how to rebalance your portfolio or how to set up your trade signals for that portfolio going forward in the future. And I had mentioned that we're trying to be quite rigorous at Applied Quantum Software, and the point of this slide is that when we perform these tests, especially our benchmark back tests, we're using all of the industry standard approaches for statistical significance. So Kupiec test, Christofferson test, Diebold test, all of those we definitely incorporate into the AQS Fabric platform to make sure that our results are statistically valid and significant. Many people ask what the future is for quantum computing approaches, both near term and in the more distant future. I had mentioned that today we can actually use these quantum-inspired approaches where we use quantum algorithms but run them on classical computers now as a bridge toward true native quantum computing. In the current era of quantum computing is called NISQ. So NISQ, it stands for Noisy Intermediate Scale Quantum Computing. So the kinds of quantum computers that we connect with, and for example, IBM Quantum Platform, we connect directly into IBM Quantum Cloud. Those QPUs, the quantum processing units, are still noisy. They're not fault tolerant. We can do some experimentation, but what we really need is over on the far side of this line, the purple dot, which is reliable, fault tolerant, error corrected qubits that run on these quantum processors. That will enable us to run our algorithms all the way to completion, give us the answers that we desire. And that is when the true inflection point will occur, when the industry will provide true practical quantum advantage for our vertical and also all of the other verticals that are using quantum computing approaches. Yeah, so this kind of follows on what I was just saying. What's standing between us and true practical quantum advantage? It's mostly boils down to error correction, where the errors, the noise that comes out of these qubits needs to be corrected so that the answers that our algorithms are churning on end up giving you answers that are reliably correct. And because I know there are a bunch of students in the audience, I do want to mention there's a lot of opportunity here in terms of research and development and management of projects that all are driving the industry forward toward achieving this practical quantum advantage inflection point. And a lot of us in the industry equate it to something like the Chat GPT moment. If you remember from about 4 years ago, suddenly Chat GPT became practical and everyone started using it. We feel in quantum computing, a similar kind of inflection point will occur, and everyone is going to jump onto quantum computing, because if you don't, you'll be left with quite a disadvantage. Yeah, so if you're interested in moving forward or joining the industry, either in research, academia, or commercially, like us at AQS, you don't necessarily have to be a quantum physicist, although that could certainly help. There are so many other aspects that can be helpful, especially algorithms. There's a lack, in my opinion, of breakthroughs in quantum algorithms right now. So we can use folks who like to design algorithms. We can use people who can do software or hardware, who can manage products, who can manage projects. There are all sorts of opportunities in terms of joining the industry and moving it forward. And I will also mention that the future is not going to be just quantum computers. It's most likely going to be some hybrid of CPUs and GPUs. So GPUs are the processing units that companies like NVIDIA produce, and QPUs. And each have their strengths, each have their weaknesses, but together a CPU, GPU, QPU ecosystem will probably be the vision of what the overall future of computing will look like. I think that's enough for my presentation. Thanks for listening. I think at our company, AQS, we are building the future of finance with quantum approaches. We're very excited about it. We spend a lot of time and energy on it. And if anybody is interested in helping us out, you can contact us. Our website is shown there, aqs.one, or you can email us. So thanks so much. I think what we'll do now is have our co-founder Jundao talk a little bit more about some of the research he's working on, which is quite fascinating. And then I think we can open it up for Q&A and see how much time we have left. So wiser folks, I think I'm going to hand off my presentation over to Jundao. So I'm going to stop sharing my screen.
Thanks, Tom. Yeah,
Hold
I'm going
on,
to share
I need
screen.
to stop share. Okay, Jundao, I'm handing it over to you.
Sounds good. So I should be sharing the screen now, and let me go full screen. Is the slides good?
Yep, all good on our side. Thank you.
Okay, great. Yeah, I'm Chuntao Zhou. I'm an associate professor at the USC, working on quantum stuff. And I'll be talking about, some of the R&D efforts we are working on. However, due to proprietary reason, we cannot really talk too much about the latest developments, but I'm going to focus more on the foundations where, leads us to these recent developments. So I'll be focusing on these 3 papers that our group developed at USC, which provides the necessary techniques that we are utilizing for the actual finance applications. Let me start by talking about quantum measurement. Quantum algorithms, one very important part about quantum algorithm is measurement, because although you can do things in superposition, solve all the problems in superposition, however, when you measure, you can only measure one branch out of the superpositions. And so you need to know how to measure to get the right information you need to solve the problem. And here are just some technical details about how we model measurements. We model it by so-called POVM elements. And we can think about measurements as using an ancilla, doing a unitary evolution, and then measuring the ancilla system to read out the result. And then one unique feature about quantum measurement, besides being so puzzling to foundation physics, it also provides genuine randomness that we can actually use. And this is actually what some people in the past has been working on, and actually still currently actively working on. This is the so-called random circuit sampling experiments. So you may recall in Google's 2019 supremacy experiments, the task is really just to generate complicated random distributed bit strings. And this is going to be just governed by, if you know quantum physics a little bit, this is just governed by these matrix elements. And these are hard to calculate classically, but easy to compute on a quantum device, because you just need to prepare the initial state in 0, evolve under the unitary, and then measure, and you get these random results. And people develop ways to characterize the quantum level or quantumness of this random distribution. For example, we care about the collision probability. And another task related is the quantum random state generation. So it is an important task because people use random states to model a lot of things. For example, we don't know what's going on in black holes. So the latest development is that we want to model black hole as a complicated many-body interacting unitary dynamics. And we try to, study how does information flow in the black hole. When you throw a diary into the black hole, what will come out, things like that. When you have entanglement between the black hole and outsiders. So so one task important is to generate random ensembles. And we hope to generate genuinely random, not pseudo-random, because we are doing quantum measurement here. And here are some mathematical details of how we measure the randomness of the quantum states. We utilize tools called the frame potential. So essentially, when this frame potential equals some value, we can certify this is, up to k moments close to the hard random states, or the, ultimate randomness you want for quantum states. So previous approaches involve things like just doing pseudo-random. For example, you can do classical random initialization of these circuits, and then you use these random quantum circuits to prepare different random states. Every time you prepare one, you need to reinitialize every parameters and generate a new state, and it's pseudo-random. Another approach is called deep thermalization. So you just, in order to generate a random state for this, let's say this single qubit, you introduce a large ancilla system here and then interact them through a quite complicated unitary. However, after that, you just need to measure these ancillas, and post-selected on a certain measurement result, this system qubit will be in a pure state. And this ensemble you generate from measuring different results forms a pure state ensemble. And this, you can show that if this ancilla is large enough, if this unitary is complicated enough, this will be approximately random in high quality. However, immediately you see there's a shortcoming where you need a huge ensemble, huge ancilla to enable the random ensemble generation of even a single qubit. And this is not very nice. So we developed this so-called holographic idea of quantum circuit sampling to enable, let's say, randomizing these qubits with a very little amount of ancilla qubits. For example, if we just have one ancilla qubit in this case, let's see what we can do. We can interact with a single 2-qubit gates fixed, and then we measure, and then you have one state becomes a random 2-state, because you measure a single qubit, you have 2 outcomes, you have 2 possible states. Then you can reset the qubits, interact again, and then measure, then you have more states. Here, technically, it should be 4 states, but figure is just for schematic. Then when this goes on forever, you will have many, many possible output states. And we theoretically prove that this will be able to generate the hard random ensemble similar to this the other approach where you have actually just a lot of ancillary qubits. So this is representing an idea of holographic circuit design, mapping the spatial direction of many ancillary qubits to the time direction of reusing the qubits by mid-circuit measurement. And mid-circuit measurement is actually quite important these days because error correction, the roadmap towards fault tolerance relies hugely on fast, high-quality mid-circuit measurements. And here we use mid-circuit measurements to also design quantum algorithms to save you space. And there was some mathematics about proving, they actually converge pretty fast towards random ensembles. And this is the experiment we did on IBM quantum device. We used only 8 qubits in the last experiment. We did a 4 qubit, 6 qubit, and 8 qubit experiment, and we are able to randomize the maximum of 5 qubit state with only 3 ancillars. So the system itself is actually larger than the ancillar, which is not possible in the previous approach of deep thermalization. And these are curves verifying this distribution is actually according to the theory. So if this agrees with the theory prediction, you are going to test that this is indeed random. And compared to the previous experiment, people are able to actually randomize helper space of dimension 5, which is between 2 to 3 qubits. This is because these are atom experiments. So there are certain atom constraints on the available states. So one atom might not exactly be 2 levels. So in this case, you have 10 atom system, but you can only do 5 dimension, means it's 2 to 3 qubits. While here we can do 5 qubits with a total of 8 qubits. So this represents an advantage. And and then you can utilize this kind of circuits for not only generating random stuff, but you can also use this for learning, for example, generative learning, because you can train these circuits towards generating the type of states you want. And this is recent work we did developing a quantum version of the classical diffusion model. And you might have heard about diffusion model, and they're used in a lot of classical AI applications. And the idea is also pretty nice. You start with things like picture of cats and dogs, and then you slowly add noise into the system until the picture is entirely random. And then you develop a reverse diffusion process such that this picture starts from fully random and slowly becomes less random. It becomes another cat. And this new cat or dog picture might be different from the one that you originally have. And this is so-called reverse diffusion. And this is possible because you use data to enable the training. So all the information about the data ensemble are stored in the things like the score function. Essentially, it's like a potential you develop such that these local minimums are the cat and dog pictures. So you can essentially, it's like a annealing, but in the simulated space. And we used this idea for the quantum case as well. And then we developed this forward circuit, which is scrambling. We add a noise to the quantum state slowly to make it fully rendered. Reverse step, it's denoising through training these parameterized quantum circuits with mid-circuit measurements. And again, these mid-circuit measurements allow us to tackle a large system with very little number of qubits. So this is NISQ practical. And I'll just finally mention how we would apply these to potential applications in finance. I will use previous published results by others, which is using this generative learning idea to essentially learn correlations between potential stocks. For example, these are just a tort problem between Apple and Microsoft. And people are limited in the number of stocks you can capture because you just have a few qubits, right? Maybe 10 qubits, maybe you can capture 2 stocks, 20 qubits, maybe you can capture 4. So it's quite limited in the past. And these are some statistical tests verifying that is working. And so at AQS, we're going to develop algorithms that can actually tackle very large problem size, like hundreds of stocks, and or generating time series of stock with very large time span. And we have results on that, which I cannot talk for now. Hopefully I can talk in about 1 to 2 months. So yeah, I will stop here and just say that here at AQS, we work both on NISQ type of algorithms and also quantum-inspired algorithms like tensor network simulation. And we also have pipelines to fault tolerance, because all these NISQ algorithms, once you develop and apply that onto a fault tolerant computers, it also runs and also gives you results you want. besides all the other nice algorithms that Tom already talked about. I think I will stop here and yeah, we can answer questions if you have any.
Cool. Thanks, Junta. All right, Wiser team, should we open it up for a bit of Q&A?
Yes, hello. So we're going to do the Q&A.
Hey, Rachel.
There's a few questions already in Discord for you guys. So first one here is the improvement due to the tensor network itself or simply because the Gaussian assumption is too restrictive? How would your model compare against a non-Gaussian distributions like students T or A stable models?
Well, that is a amazingly excellent and technical question. So I can approach that from a high level, and maybe Jundao can approach it from a more detailed level. One of the advantages that we're trying to provide with AQS is to capture correlations and distributions that are not represented by a simple Gaussian model. So for example, if we're looking at a correlation matrix or a covariance matrix between the movements of the returns of various stocks, like Jundao mentioned Apple and Microsoft. So if you put together a giant covariance matrix that maps, that does a pairwise mapping between the returns between the time series of those returns, you will get useful information. And today in the industry, that type of information is used to do modeling of risk and optimization, etc. But with quantum approaches, we can take that a lot further. We can do higher order correlations between these different series of numbers that you couldn't otherwise do with classical approaches. So we can find correlations between groups of, let's say, stock prices. So maybe Apple, Google, and Microsoft, as they move together, and compare that with something totally different, like energy prices or something like that. And we can find these really esoteric hidden correlations that you can't otherwise do with just simple, not simple, but with standard approaches like regular, like Gaussian or a regular covariance matrix. So I think I'll stop there.
Yeah, I think Tom did a very good job. Yeah, so we hope this tensor network can capture things beyond simple correlations, and especially under in extreme conditions, rare events really happen because of very complicated multipetide correlations, and these can be captured by tensor networks and also NISQ quantum approaches better than the traditional approaches.
All right, so the next question we have here is, in portfolio optimization, do you use any AI ML stage where models are trained on the market data before it's passed on to the quantum solver?
Also, these are great questions. The answer is yes, it's possible to do. Yes, we can do it. But honestly, no, we're not doing it right now because we're focused so much on the quantum approaches. We haven't integrated what you're talking about, which is sort of a hybrid machine learning and quantum approach together. We're just starting to do that. And there are some really interesting recent papers in the industry. There's one, I think, with IBM and Vanguard, and another with IBM and HSBC, where they are integrating machine learning approaches with classical financial algorithms. Like, let's see, when they were trying to train for trade execution, they were trying to come up with models of how best to price bonds. And they were using machine learning to come up with data sets that are optimized that could then be fed into the quantum approaches. So definitely that is one of the cutting edges of what's happening in quantum finance right now. And absolutely we'll support it, but we're still a startup, so we have limited resources, and we're focusing more on the quantum stuff. But that should not. On the other hand, though, I must say that a lot of the research that Jundao is doing right now is specifically for quantum machine learning. So we are, as Jundao and his research team make more progress, we are incorporating all of their results and findings and applications into the AQS Fabric platform. So we're getting there. We're making progress.
All right, excellent. So now this question we have, your roadmap suggests that future systems will integrate CPUs, GPUs, and QPUs. Which aspects of your company's core mission require quantum computation, and what limitations of current GPU-based computing make quantum processors necessary for those workloads?
Quantum computers are a specialized tool, and they are not general purpose computers. They are not general purpose GPUs. They have specific capabilities that solve specific kinds of problems. And on one of my earlier slides, I showed some of the different categories of problems in finance and that we have found to be amenable to quantum computing approaches. I mean, there are a lot of other use cases in finance that are not applicable. So quantum computers need to be part of this tool chain where they're used for to provide their specific advantage. So let's see, what's a good example? So maybe in terms of the CPU, GPU, QPU tool chain, we would end up doing something like, oh, let's mix in the machine learning part. We might use GPUs to do some of the data cleansing, feature selection, that sort of thing that then feed into a quantum machine learning algorithm that's optimized for training and inference that can perform those functions of machine learning training and inference faster than you could otherwise do on the GPUs. So that would be an example of where the integration might occur. Hopefully that answers the question a bit.
All right, this question here, what type of noise are you trying to mitigate in the forward-backward noisy diffusion process via scrambling? Is it noise in phase or some other type of noise?
Great question. Junjao, that one's for you.
Yeah, so we can add a different type of noise. And one important thing is that these noise are actually added by ourselves to enable generative learning. Like the classical diffusion case, you are intentionally introducing randomness into the data such that you see how the data evolve from structured data to entirely random data. When you observe this forward process in the reverse step, you know how to remove noise. And then you can start from another generated noise, and then doing the reverse noise removal, you get the structured data. So these are like intentionally introduced noise, not the device noise themselves. So in fact, the device noise themselves, it's probably not going to be helpful for these generative learning tasks either.
All right. If anybody has another question right now is the time to ask, and then we're going to wrap up with these speakers and we'll move to our second speaker of the day. There was one question back here that I can ask in the meantime here. Where did it go? Since currently quantum computers are noisy and error prone, what are the real world problems they are solving today?
Right now, in the NISQ era of quantum computers with the noisy QPUs, there is honestly not a lot of practical quantum advantage that's occurring right now. So much experimentation, so much setup for the the day when the actual QPU's hardware is mature enough to not be noisy, to be fault tolerant, and to allow our algorithms to run all the way to completion. So what we are our target is the fault tolerant era, the fault tolerant regime of quantum computers. And when you look at some of the quantum hardware vendors' timelines, that day is coming rather soon. So we like to look at IBM's timeline. I mean, there are others, there are IonQ and others, but IBM has proven to be pretty reliable in sticking to their projections. So they're telling us that in 2029, they will be able to provide a quantum computer with 200 qubits, but actually 200 logical, error-corrected, fault-tolerant qubits. And when that day comes, a lot of our algorithms will immediately become practical, and we will start achieving practical quantum advantage over classical approaches. So that's a day that we're targeting. There are other quantum vendors who have more aggressive roadmaps. We're trying to be conservative, and that day of quantum advantage could come sooner because there's a lot of investment, time, energy, resources being amplified onto this problem. So don't be surprised if the logical qubits come sooner than some of these conservative roadmaps are currently projecting. Jundao, did you want to add anything to that?
Yeah, I think we do want to target at the fault-tolerant area, and then we want to be quantum ready for that. And for practical applications in the NISQ area, it's actually an open question right now in both academia and the industry. There were advantage experiments like random circuit sampling, which random, so there's not much real application in that. However, at AQS, we aim to develop real applications for NISQ as well, but that will be narrowed to specific applications like generative learning that I was talking about. For vast other applications, we do need, fault tolerance, and as Tom said, we need that to come in a few years. Yeah.
All right. We did get one additional question. In the absence of fault-tolerant quantum computers, how many qubits are sufficient for simulating quantum routing problems, algorithms involving datasets for delayed tolerant networks / autonomous vehicles while tackling optimization problems in the NISQ era?
A great detailed question. Currently at AQS, we are connected into IBM Quantum Platform, so IBM Quantum Cloud. They are providing us with QPUs that have 156 qubits. These are not error-corrected qubits, and we're running a lot of our experiments on those machines. So if we take some of our algorithms and scale them way down to like very, very simple problems, we can get some of them to run even on those NISQ processors. But to properly answer your question, I really think we're going to need to get to the age of the fault-tolerant logical qubits. So that's what the industry is driving toward. But you know what, Rachel? I noticed that the next speaker is Bob Wold, and we are actually partners. So Quantum Rings and AQS have partnered together. So this is going to be a great segue from us to them. We actually, when we're not using IBM Quantum Platform, we're using Quantum Rings as our quantum simulator. So our AQS platform connects right into Quantum Rings, and we can run a lot of our algorithms on using their simulator. So it's a kind of a perfect segue.
Wonderful. Yeah, Bob has arrived and we are done with our questions, it seems. So I would like to thank you again for joining us today, guys. We appreciate it. It seems like everybody really enjoyed your discussion. And if you can send me slides so that we can add them to our online learning platform for students to assess later, that would be great. But yeah, we appreciate your willingness to chat with us today. And yeah, so we're going to say adios and we'll welcome Bob.
Cool. Thanks, Rachel. And hello,
Yeah.
Bob.
Thank you.
All right, I'm going to sign off, Rachel. Thanks so much.
Yes, thank you.
Yeah. Thanks, Tom, for the quick shout out. That was cool to join at the tail end of your presentation. Yeah, Tom and AppQSoft are pretty awesome, especially when it comes to anything at the intersection of quantum and finance. So tap into that resource if you can.